Okay, the clock says it's time to get started. So, welcome everybody. I am Björn Fahller. I will be of this stand-up comedy session about Typesafe C++. We're going to have a lot of fun at the expense of this language. A bit of background: I've been doing software development as a profession since '94. So I guess I'm getting a bit graybeard. I think I wrote my first C++ program in '93, might have been '92, not entirely sure. So I've learned a lot about how to abuse things. That is kind of what I like to do. But today we're not actually going to abuse things. We're going to have fun at the expense of a very unsafe language, and it'll be a blast. All right, so what is type safety? I mean, to be able to talk about how to achieve type safety and what is good and what is bad, we must have an idea of what type safety actually is. Anders?
The language isn't too happy about converting types without you say that makes it safer.
The language is not too happy about converting between different types. Yeah, that is definitely one of them. Other ideas for what makes... At compile time, the compiler can tell us what is a valid action or not.
Can't write arbitrary data to an arbitrary address.
Cannot write arbitrary data to an arbitrary address is a good one, especially in C++. Here's what the Wiktionary says. Type safety, the extent to which a programming language discourages or prevents type errors. I think this is really interesting. The extent, that is, we can have very little type safety, some type safety, quite a lot of it, or extremely much type safety, and also discourages or prevents. We can have a system where you can do all crazy things, but it's sort of cumbersome. And I guess that is where C++ comes in, because after all, we can, as you said, Alf, we can do arbitrary writes to addresses. We can do type punning via void stars and what have you. So there's absolutely no way that we can prevent. We cannot protect ourselves against Machiavelli, but we can protect against honest mistakes. So here's my take of this. A type-safe system discourages or prevents use of one type when another is intended, as was suggested, and also prevents or discourages operations that don't make sense. Who here is familiar with the POSIX APIs? File handle. What operations make sense to do on a file handle? +1, yeah. Yeah. Doing arithmetics on file handles, that is a really good thing. So maybe not a great example of good type safety. Also, use of values outside the defined space. I remember when I was a young teenager and I was first introduced to Pascal. And you can say, this type is an integral type that holds values between 1 and 6. Perfect for modeling dice. As one example. There are probably other ideas, but I think these are the most important ones. So this is actually what I'm going to talk about today. I'll sort of sneak through the introduction without saying anything. So we're going to look at type safety in C++, the raw language itself, what it offers. And then I'm going to show a fairly simplistic, but nonetheless quite powerful library solution. And then scout GitHub for some more sophisticated libraries to achieve type safety. And at the end, we'll look at what happens to your code when you use strong types that are genuinely safe. Because things actually happen to your code. Good things. So, my story begins with this extremely embarrassing bug. I was a team lead of a number of programmers. We were developing a communications protocol for directing data flows through a network. And we have in this example, I want to initiate a remove of a receiver from a data flow, and all these messages have a request ID, so that when you get a response, you can map the response to the request via the request ID. And in this case, you also have a receiver ID. And both of them are represented as 32-bit unsigned integers. And do you spot the bug? Yes. Oh boy, did I feel embarrassed. Oh. Have any of you made this kind of mistake? Yeah. What did you do? What I did was I started wondering, when is it allowed to, when can one type be allowed to use when another is intended? So if we have this code, like here, we have a function that has a B, and it wants to call a function that requires an A. When is this allowed? And in this case, we can actually not say this, because we don't know what A and B are. But what about this? A and B are structs that they are in every way the same type, aren't they? They are naked structs. They have exactly one member called value, and the type is the same as int. So is this legal? No, it's not legal, because they are different types. Good. So what if I actually want to make this legal then? Can I do that? Well, I can add a constructor to A that takes a B, providing I'm not marking it as explicit, because if it's explicit, it's still not allowed. Or I can add a conversion operator from B to get an A, again, as long as I'm not marking it explicit. Or I can change the inheritance structure so that a B is an A, then it's also allowed. And in all other situations, this is forbidden. It's not allowed. So with this insight, a slightly different story began, where instead of using type defs for request ID and receiver ID, I just made naked structs that holds a value, and I made this mistake, and boom. Candidate function not viable. No known conversion from receiver ID to request ID. Hey, we're at home, dry. This is it. Except it's a little bit cumbersome to work with it this way, with having to access dot value all the time. But this is a good start. So this means that for types that we create ourselves, we have full control. Everything is forbidden by default. If we want something to be allowed, we must make an effort to allow it. This is great. So what I did then instead was to make a class for receiver ID, so we can construct it, we can get the value out of it easily. Having the ability to compare for equality makes sense, and we're actually using these in a map, so the less than operator is also good. But this becomes a lot of boilerplate. And especially since I'm going to repeat exactly the same thing again for request ID. So we have a solution, but it's a bit cumbersome. I don't want to write this code over and over and over. So what happened then was I started thinking about, can I write a library for this? And since you already saw the agenda, you know that we can, or at least you assumed. Before I go on, are there questions about what I've shown so far, or is it clear? Okay, I see nods. Good. So I started experimenting with something like this, a class template that takes a T as the type that it's to represent, and the tag. I'll get back to the tag very shortly. It has constructors from a T, and you can get the value out of it, and you add other operations, the equality, comparison, less than, what have you, assignment. You may note that tag is actually not used for anything. It is actually used here to prevent operations. So here I'm saying explicitly that a safe type is not allowed to be constructed from a safe type that uses another T or another tag, or both. And the same is repeated also for, at least for assignment. And you can use it like this. Using int1 is safe type of int and struct int1 underscore. So I'm creating here the struct int1 underscore, that is the tag type. It's not used for anything anywhere in the program other than to make a difference, to make sure that int1 and int2 are actually different types, because although both are safe types of int, they have different tag types. And this works. This works fine. So by changing my code so that request ID is now a safe type of uint32t and request ID tag, and the same for receiver ID, but note that the tags are not the same. They're different. So it's not allowed to mix these. So with this bug, again, the classic, we get this compilation error. Candidate function not viable, no known conversion from safe type blah 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 receiver ID tag to safe type blah 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 request ID tag. This worked. It's not ideal, but it's good. It's a bit noisy, the error message, I think. So we can do a little bit better. Are you familiar with curiously recurring template parameter idiom? I got to write this one, Peter. Does this look familiar to you, or is it weird that request ID is defined in terms of itself? So the request ID inherits from safe type of uint32t and request ID. The reason this works is that safe type doesn't actually do anything at all with the tag type. It just needs to know that it is a type. And when you have struct request ID colon, no, request ID is known to be a type. We cannot do much with it. We cannot instantiate it. We don't know how big it is. We cannot call functions on it. But we can use its type. We can have pointers to it. We can have references to it. We're not doing that, but we can. And in this case, I can use it as a tag type. And then we have the using directive to say that request ID has all the constructors that, that the safe type does. And repeat the same thing for receiver ID. And now we see candidate function not viable, no known conversion from receiver ID to request ID. Perfect. Absolutely perfect. Peter, I'm going to have to ask you to close your eyes again. I'm sorry. This is a little bit too much boilerplate to repeat, so I made a convenient macro. I really am not a friend of the preprocessor, but sometimes it can provide conveniences. So by using this, I can write safe type request ID uint32t. The syntax is wrong, but it is convenient. It's not a lot of typing. It was not difficult to convince my colleagues to start using this, which prevented a huge number of bugs. So now you've seen how to write a simple library. This was actually used, or is still used, at my previous job. It's good enough for a lot. Questions, or can I go on? So let's take a look at what others have done. There are several libraries available. I will briefly introduce you to two of them. There are others. This young man came along, Jonathan Miller, Foo Nathan on various social media. He posted on his GitHub account this Typesafe library. 0 overhead utilities for preventing bugs at compile time. I think I'm sold already. This is a fairly rich library with which you can piece together the functionality you want of your types. It also includes a number of other things that you may argue don't really have anything to do with type safety per se, like variations on optional and variant that actually don't know to which degree they differ from the standard implementation, but they are available from C++ 11. So at least that. It looks like this. In the header, typesafe/strongtypedef.hpp, you have a class template that the public interface looks like this. You can create them from your values. You can get the values out of a safe type using a conversion operator. Everything is const expr, everything is explicit. And you see on the first few lines that it's pretty much the same idea that I had. The template parameters are in the reversed order from my example, but it's the same idea. And the way you use it is like this. You include the header, obviously. You follow the example in Jonathan Miller's documentation and get a shorthand namespace. And you say, my handle is a type-safe, strong type def for my handle. And this is now really just a handle type. You cannot do, the only thing you can do with this is to create it with a value, and you can get the value back. That's all. But here comes the stroke of genius. He's a very clever young man. There's a sub-namespace, strong type def op. And with that, you can piece together the functionality. So you can say, yeah, and by the way, I want my handle to be equality comparable. And I want to be able to stream it to O streams. And there are also some functionalities that are of a higher level functionality, like integer arithmetic. This is probably going to surprise you. When I've used strong types in my code base, I have not once found a need for an integer arithmetic type. I have found a need for something else that I will get to, because arithmetics is needed, but I haven't actually needed an integer arithmetic type. Since you define a struct, you can of course add your own member functions to it as you please, or in this case, maybe I don't like the stream insertion operator that is provided from the library. I want my own, so I can then just write the member there, and I can get the underlying value by using a static cast. Or, since this is actually rather cumbersome, I can use from the library the function get. Get is overloaded for constant, non-constant, L-value reference, or value reference. It does the right thing. So that is handy. There's another one that is also worth looking at. This is a bit more modern. I think it was roughly a year ago that Jonathan Bucara posted his library called named type. So implementation of strong types in C++. So you have the GitHub link there. It's a much smaller library, much more focused on type safety. But of course there are some other sort of related things, like support for converting between like but not the same types, like meters to feet, for example. And if you have not watched his talk from Meeting C++ last year, you should take a photo of that link. It's an amazing talk. His library is similar. I'm talking a little bit so that people can take photos. similar, but not quite the same. You can see that it is a bit more modern. We're done? Okay. So the way you use it is, well, you recognize the pattern. It's my handle is fluent. Everything is in namespace fluent since he's using it in his Fluent C++ blog. If you're not reading that, you should. So it's a fluent name type of int and a tag. The difference here is that the functionality you want, Jonathan Bokara calls this skills. You add them as parameters in the template parameter list, which means that you don't have to repeat and say that comparable, my handle inherits from comparable my handle. So you get it's a bit shorter. If you're reasonably familiar with writing template code, it's not difficult to add your own skills. The same actually goes for Jonathan Miller's library. You can, if you like, use the CRTP instead. The advantage of doing that is, of course, if you want to add member functions. He has one thing that I think is a little bit questionable. You can say that, actually, I want my type to be implicitly convertible to something. I'm not sure that that is a good idea, but it is at least good that if you want it to be implicitly convertible, you have to be very explicit about it, and it's also but ugly. And that is good. And that's pretty much it, actually. I'm not going to mention more, but then now you have seen two examples that are available from GitHub. Questions? So what do you think happens with your code when you start using strong types? It won't compile. That is what happens. Yeah, because your code is bug-ridden, and the compiler will now tell you that your code is bug-ridden. Fix your code. Yeah, that is true. Can be true. Doesn't have to be. I'm using an example from my previous job. I worked for NetInsight. NetInsight makes networking equipment, and NetInsight prides itself, rightly so, of knowing exactly how much network capacity is utilized on every leg in the entire network. And the way this is done is by using I'm simplifying here, but it's a quanta of network capacity that is called a slot. And slots are grouped together in frames. Frames are typically 1,000 times bigger than what I'm showing here, but you would not be able to follow those slides if I drew them correctly to size. And these colors here are data flows on a leg in the network. So we can see that we have a green data flow that occupies 8 slots. And we can see the exact indices. And we have a much smaller blue data flow. And we can say that the white ones are unutilized capacity that we can add for new things. Slot ranges is really important because NetInsight needs to do set arithmetics actually on these. And like I said, the frames are much bigger than this, and you have many, many, many instances. So by being able to represent a continuous range as just 2 numbers saves a lot of computation and a lot of memory. So those are important. And they're represented like this. The 2 boxes on the left are pseudocode. You cannot just forward declare an anonymous type like this. Unfortunately, I would really like to see that true. But I don't want to get into how they are represented. But the indexes identify a slot in a frame, and the slot count is just the number. And then the range is something that has a start and a length. So, for example, in the picture of the frame, you have the green one on the right. It starts on slot index 13 and has a slot count of 4. Okay, so Magic numbers. Don't we hate those in our code? We have something like this. Establish a connection on SDI. SDI is an old video transfer standard, constant bitrate. So we say create connection destination 528. What is 528? So I have to read create connection prototype, and I see, okay, it's a slot count 528. Okay, good. But with a reasonable strong type support, you will not get away with this. The compiler will say, no, I'm not doing an implicit conversion from a naked int. Sorry, you have to state what the type is. So by saying, at the call site, create a connection to this destination with a slot count of 528. This is not great, but it is better. Because now I'm expressing intent, and we know that the capacity here is in slots. It's not in megabits per second or whatever. How many of you, since we're in Norway, how many of you write your programs using a Scandinavian keyboard layout? You love curly braces, don't you? So just to save your hands from falling apart, you of course give it a name so you can type some fewer curly. So just by having a really programmer-hostile keyboard, you will write better programs. That is good. Who knew? So do that. Be explicit with the type and give your numbers names. That means something. All right. Encapsulation. This is interesting. So in this implementation of the communications protocol, the protocol is a binary protocol, so we want to stuff things into a message buffer. So I say that I want to serialize this capacity as a slot count as 24 bits. Needless to say, this code is repeated 3 or 4 times throughout the code base, which is completely bonkers. Fortunately, the protocol is sane, so a slot count is always represented as 24 bits. So we can do something, since using a strong type, we can do something that we couldn't do with a type def, and that is to overload functions. We can say that the way to serialize data is to go through this function that is called serialize data, and it is overloaded for slot count, and it's overloaded for slot index, and for receiver ID, and for request ID, and you have the information of how to represent, in this case, a slot count in a message buffer in one place, in the serialized data overload for that type. And of course, then you do a convenience thing and offer a templatized serialized function that just calls this serialized data, so you get the code as on the last line there, where you just say buffer.serialize capacity. Now we have gained 2 things here. One is the encapsulation. We bother with how it is represented in one place. It's not distributed, this 24 bits. It's in one place. That is good. We are also much more honest about which level of abstraction we're working on. Here I'm building a message. I'm concerned with which parts does this message consist of? What data is stuffed in there? Exactly how it's represented, that is another layer of abstraction. So it makes the code less cluttered, which is a good thing. And this is a biggie, type semantics. Someone suggested an important bit is to see what operations actually make sense to do on a type. So we had something sort of looking like we have a slot pool, and to be quickly able to see if can I establish a data flow over this leg of the network. I just want to very, very quickly be able to ask the slot pool for that leg how much is available. And this is done by, for example, in the release capacity function, we iterate over all the ranges and just add to unused slots. And of course, this did not compile. Stupid system. Okay, back to naked ints again, eh? Or not. So I started thinking, what operations do actually make sense on these types? Does it always make sense to do additions and whatever? So back to this. We have a frame of slots, and I start thinking, does it make sense to add slot counts? Well, yeah, that was the example. Adding slot counts gives another slot count. Subtracting them, yes, it's symmetric. It makes perfect sense. Multiply slot counts, get slot count squared. No. Even though you're not familiar with the problem, really, you understand intuitively that this is nonsense. You don't want to do that. So no, gone. Do I want to be able to scale it, to multiply with a ratio, say I have this slot count and I want 5 times as much? Yeah, makes sense. Divide slot counts with each other, yeah. It's sort of the same thing, it gives me a ratio. And yeah, dividing a slot count with some ratio makes equal sense. So that is good. What about the slot indices then? Does it make sense to add slot indices? Makes absolutely no sense whatsoever. Slot index plus a slot count. Yes, I mentioned that when I talked about the slot ranges, consecutive ranges of slots. So that makes sense. A slot index plus a count is another slot index. So again, for example, the green range at the top right, 13 plus its count of 4 is 17, which happens to be where the next range begins. Can we subtract slot indexes? Yeah, sure. Makes sense. Gets the slot count back. Divide slot indices. Divide with the slot count. This is getting weird. No, I don't want that. Divide with some ratio. I have the 16th slot and I want to divide that by 3. No, that doesn't make sense. Slot index squared. No, go. Slot index times slot count. No, go away. This is nuts. We don't want that. Slot index times a rate. No, go. Does this remind you of something? You should actually recognize this pattern. The absolutely perfect example is in the chrono library. The counterpart to the slot indices are the time points in the chrono. And the slot counts on the left, its counterpart in the chrono library are durations. I can add durations, I can scale durations, I can subtract durations, I can add a duration to a time point to get another time point. I can subtract 2 time points to get the duration between them. Another example that is almost correct, but not quite, is pointer arithmetic. So you can say that on the right-hand side you have pointers, and on the left-hand side you have the int type. The only reason that that is not exactly correct is because the int pointer t is a generic integer type that you can square if you like, which doesn't make any sense, or close a file with. I did not know this, but this is actually, there is a name for this in mathematics. This is called an affine space. So the typical idea of an affine space is a coordinate system where you have positions. The positions are, in this case, the slot indices. And you have vectors. You can add vectors, you can subtract vectors, you can add a vector to a position to get another position. If vectors are parallel, you can ask if one is longer and shorter than the other, how much. You can get a new vector by saying this vector times 3, so it's a 3 times as long vector that is parallel. So So I discovered something that is, of course, well known since a long time. But it's good to know that my intuition was onto something. So I actually modeled exactly this behavior into slot count and slot index. And don't you think I actually discovered a bug where I made an operation that did not make sense? Yay, strong types. So test code then. Test code is interesting. So we have something like this. We have a test capacity decrease is notified to clients. So in this test, I have a test node, and I'm creating 2 clients. And at the end, I'm throttling the capacity, and I want to make sure that a new capacity callback is called. But what are these numbers? It's a bit confusing, isn't it? But we all heard that it's bad to use magic numbers, so let's name them. This number 4 that comes up, it seems to be a request ID. Let's do that. Request ID 4, yeah. So the code is a little bit cleaner now. Maybe I should do the same with the other numbers. So I give them names as variables too. Don't do this, for love of everything that is sacred. Don't do this to yourself or to your colleagues. This code was almost good, and now it's completely impossible to read, even though it's just straight code. Just don't. Personally, I actually like magic numbers in when we're talking about example-based tests, that is. But I want to give them a semantic meaning that tells something to me. So I prefer to write like this. Create a client with capacity of slot count of 5 and another with a slot count of 8. The advantage of this now is that the code speaks to me as a reader and says, I know what the units are. And if I'm getting these wrong, I get a compilation error. But since this is an example-based test, it's also much easier to reason about the validity of the test, because I can see that at the end I'm throttling the capacity to 5. And the thing I'm checking for the callbacks is that I get a slot count of 2 and 3. 2 plus 3 is 5. So yeah, that makes sense. It's probably true. And I initialized the clients with 5 slots and 8 slots. So 5 to 2 and 8 to 3. It feels like it's a fair scaling. So this is probably a reasonable test. So I actually like magic numbers in example-based tests, but give your numbers a semantic meaning. You can, of course, do this with even if you have type defs, but you won't. I know you won't, because the compiler will let you get away with doing the wrong thing. In this case, you have to. So you're forced to write good code. Yay, strong types. So that is actually what I wanted to talk about. To summarize, we all know that the type safety for the built-in types, it's absolutely terrible. You get implicit conversions to everything. But structs and classes are as strong as you make them. Everything is forbidden by default. You must explicitly add the functionality that you want to have. And as we saw, there are some libraries available that can make your life easier. And like I showed with this affine space types, where I have 2 types that are coupled and mean something together. Just reasoning about this helps you understand your problem better. And if you can model this in your type system, you prevent the possibility of making mistakes. And beware of the urge for convenience, like the implicit conversions, because it is much more convenient to write code like that, and you have just blasted a hole through the entire ID, because now things can implicitly convert to something you probably did not want, at least in a place where you probably did not want it. So be a little bit careful about that. And strong types leads to more expressive code. You have fewer magical numbers. And you have better encapsulation because you can overload on them. And your tests express intent much more clear to the reader. And avoid type defs. Type defs are really handy locally inside a function to create a shorthand, but don't use them in your APIs. Because really what the type def, when you use it in an API, it's really just a comment. It says, yeah, it's an int, but use it in this way. Who reads comments anyway? So be careful about that. And that is it, unless there are some interesting questions. Yes?
Have you tried using user-defined literals? Does that increase readability?
Can you repeat the last bit? Yes?
Have you tried using user-defined literals instead of
Yes, have I tried using user-defined literals instead of explicitly writing my type? Yes, I have. It's a matter of taste. Actually, in the very long version of this talk, I had examples of that, but 45 minutes is shorter. I had to strip some things. More questions? I want to show you one thing. There are a few minutes left. Are you concerned about performance? A few nods. Simplifying a bit, but you recognize this safe type here. We use a T and a tag. Can construct it, I can get the value out. I've added an operator plus equal and minus equal. So I'm using some safe types here, int1, int2, int3, that uses different tags. And I've created an addition that you can add an int1 and int2, sort of like the slot index plus slot count to get another slot index. So I have a function here that takes an int1 and int2 and calls consume on the sum. And here is the horrible overhead that you see. There is none. There's absolutely none. The compiler sees through everything. It's just an addition of two registers. It doesn't get any better. But it actually does get better. Because here I have another function, a safe function that takes by reference an int1, an int2, and an int3. So we add to I1 and we subtract to I1, and we see that it creates a function that does a move, add, sub, move, return. Okay? And then I'm mirroring the same thing as a primitive function using the primitive types. So these are just then aliases for integer references. And it does exactly the same thing. But look at the code. Move, add, move, sub, move. It's one instruction longer. How come? Any ideas? Tony knows, of course. Yes, aliasing. The rules of the language say that two pointers, or reference in this case, of different unrelated types must not refer to the same object. So the compiler knows that there is absolutely no way that there will be unexpected side effects of these I1, I2, I3 actually being the same variable. It knows that they cannot be because they're different unrelated types. Whereas in the primitive function, the compiler must assume that it is perfectly possible that every single one of them are the same. So, yeah, we have a negative cost abstraction. Who heard of that last time? Yeah, this is a good one. I must admit that this is rare. I actually had to work a bit to come up with an example that showed this. But don't be afraid of using strong types for fear of performance loss. Don't use strong types expressively to get performance gains, because you may be disappointed, but you should absolutely not expect performance loss. and you get much better code and much better safety. So that's it. The top link is to an experimental library that I have written. Please toy with it if you like. Unlike Jonathan Miller's and Jonathan Boccara's library, it does actually support affine space types. The second link is to where my slides for my talks are, including this one. I uploaded it during the lunch. So go there if you want to. And then you have information for how to spam me if that is your thing. Thank you very much.